In this video, we'll talk about what I'll call analog I/O handling, and just a look at when the analog signal, the 4 to 20 milliamp signal, comes into the PLC. How does it get handled by the PLC? So in the last video, in the 2.5 analog I/O devices, we spent a lot of time talking about the devices themselves and the 4 to 20 milliamp signal loop, and just kind of the transmitter receiver aspect. So again, the PLC would be considered the receiver, and then of course the process transmitter is the transmitter. It's putting the 4 to 20 milliamp signal out. So we know that from that previous video that the the actual engineering value itself gets uh, uh, transposed from the engineering unit into a electrical value of a 4 to 20 milliamp signal. So for example, the temperature, again, if it's 0 to 100, that's an actual real world value, 0 to 100 degrees Fahrenheit. It gets converted into an electrical signal that will now get transmitted on that wire from the transmitter, and that is a 4 to 20 milliamp signal. So 0 to 100 degrees Fahrenheit now gets converted into a 4 to 20 milliamp signal, and that is a linear conversion. All right, so it's basically scaled. 0 to 100 degrees Fahrenheit would be equivalent to 4 to 20 milliamps as a transmitter output. So just to kind of show that loop one more time, the receiver, the PLC. So here's an example of this diagram is just the Siemens PLC analog input card over here. But we've got our process transmitter, and we've got our loop going. We do have a power supply or power source in the loop. So it's going to be our two wire transmitter loop. But the power source into the transmitter, out of the transmitter into the receiver and back. So that gives us our loop. Our actual physical stuff is connected through here on this transmitter, and then it gets converted electrically and sent out on the loop. Being that this is a flow, this kind of gives the impression of like a flow transmitter. But anyway, so 4 to 20 milliamps again gets received in the PLC. So what happens when the PLC receives the 4 to 20 milliamp signal? It again has to convert that into another number or value that the PLC can understand. So we've got quite a few conversions happening here. One is real world measurement converting to electrical 4 to 20 milliamp signal, and then we get to the PLC, we convert again from 4 to 20 milliamp signal into a digital numerical representation. So we call that an A to D converter, what happens inside of this analog input card. A to D standing for analog to digital converter. So the A to D converter is like a little chip on the card, and it can detect the current, and it basically takes the current value, and again it knows that there's a high and a low end to it. It knows it's going to be a 4 to 20 milliamp signal coming to it. So 4 milliamps would be the low end of the scale, and 20 milliamps would be the high end of the scale. And then it basically says, okay, if you're 13.65 milliamps, then it'll get converted into an actual digital number inside the PLC. So this chart kind of shows that a little bit better. So again, I said it's a linear conversion, and that is true. So basically, if we think about this 4 to 20 milliamp signal as being a linear function, meaning that it's just it doesn't kind of do all this strange curving, or it doesn't curve like a exponential. It's just a flat linear line with a slope to it, positive slope to it. So we could look at 4 milliamps again is the low end of the actual current. So that would represent about 0% of the actual signal of whatever it is we're sensing. 20 milliamps is the top end. That would represent 100% of that signal. So 12 milliamps is halfway. 8 milliamps would be 25%. 16 milliamps would be 75%. Okay. Now, one other piece, that kind of relates back to what we talked about back in the, when we were talking about bits and bytes and nibbles. We talked about, each one of these digits in the binary number representing a power of 2. And we talked about, word length. So a analog signal that comes into the PLC, when it gets converted using an A to D converter, it's going to convert it into a word length memory, which is basically 16 bits. But again, we're starting here at 0. So this first bit would be a value of 2 to the 0. This is 2 to the 1, 2 to the 2, 2 to the 3rd, 2 to the 4th, etc. That gets us to this very last bit here, which is the bit 15, because again, we're starting with 0. So that would mean that the value of this bit and everything here would be 2 to the 15th power. And 2 to the 15th power is 32,768. So when our PLC is doing its conversion, its analog to digital conversion, it is now going to put it into a number that can be anywhere from 0 to 32,768. So again, lots of conversions happening here. So we've got our sensor input percentage. We've got which gets converted into a 4 to 20 milliamp signal, which in turn gets converted by the PLC into what we call the raw count, which is basically the direct conversion from the milliamps into a word length number. Now, of course, it would come all in as zeros and ones, like this is a binary string, but we do convert that number back into a decimal number, so we can have an easier time representing at least what this number is. Now, at this point, when the PLC receives it, it reads it and it puts this number there. This number doesn't really mean anything to us as an operator, because again, we're considering, we're looking at what we call the engineering unit. The engineering unit is the actual value of the sensor. So again, if we're talking pressure, and if the pressure transmitter is 0 to 100 psi, so 0% of that sensor is 0 psi, 100% is 100 psi, so 50% of that sensor is 50 psi, 75% is 75 psi, and 25% would be 25 psi, right? So it's just that part is 0 to 100 psi is an easy conversion. So again, if we're at half, if we're at half of the sensor input, if we're at 50 psi that we're reading in the field, that means our transmitter is sending a 12 milliamp signal out to the PLC. That when the PLC receives 12 milliamps, it's going to convert that number into the number 16,384. All right, so we either have to be smart enough to say, okay, well, we know that transmitter is scaled 0 to 100, and when I see 16,384, that means I'm at 50%, which therefore means I'm at 50 psi. Or we do one more scaling, one more conversion. There'd be another kind of column to this chart over here, but inside the PLC, we'll have a part of the program that will convert that raw count back into the engineering unit. So we call that a scaling block. Some PLCs allow us to scale the value right on the card itself. We just kind of use a configuration setting in the card and it'll scale it back to the engineering unit. Some PLCs require us to actually put something in the program to scale it. So it all kind of depends on the type of PLC we're using. But as we can see, and we'll definitely cover this as we move on in this class, but there's a lot of the analog signals can can have a little bit of complexity to them because we have just multiple conversions going on from back from the actual sensor input all the way into the PLC. But that's about it for this section, just to kind of introduce this concept to you. Once again, when we get into the analog programming part of the course, this will kind of come back and we'll kind of get to look at this in a little more detail at that point.